So we'll move on to quantum error correction now. There are several challenges in quantum error correction. So what are the challenges of quantum error correction? So challenges of quantum error correction. Well, the first thing is that there is this no cloning theorem that we have studied before. So that could come in the way of copying quantum bits. As you know that to do an error correction, we need to add redundancy. And so the no cloning theorem could come in the way of this. The second challenge is that quantum errors unlike the classical ones are continuous. So obviously are harder to correct. And the final one is that to be able to detect errors, we need to measure in the syndrome detection phase. But you know that the measurement postulate says that the measurement changes quantum information. So this is another challenge. Quantum information. Right. So those are the challenges. Now, it turns out that a large class of quantum errors can be discretized in the following sense. Suppose we have an initial state psi and it evolves along with the environment, then one can show that in a large class of quantum errors are of the following type. So it evolves into some state that looks like this. Where X, Y, and Z are the, so I should write this. This is E0, this is E1, this is E2, and this is E3. So X, Y, and Z are the Pauli matrices. And therefore, since Y is equal to minus I times XZ, effectively all quantum errors are either bit flip errors, which is denoted by the Pauli X matrix, or phase flip errors, which is denoted by Pauli Z matrix, or a combination of the bit flip and phase flip errors. So therefore, when we do quantum error correction, all we need to do is to have a scheme that corrects the bit flip and the phase flip errors. All right, so that having been said, now let's see how we can devise a protocol to correct bit flip errors. So quantum error correction for bit flip errors. And this will be similar to the classical errors. We are going to add some redundancy. So, and we are going to assume that only a single bit flip error occurs. So this protocol that we're going to study is going to be able to correct only single bit flip errors. So we have an initial state psi is equal to alpha ket 0 plus beta ket 1, and we encode by adding redundancy, and we will convert this to alpha 0 0 0 plus beta 1 1 1. And so the encoding circuit looks like this. So we have just like before, we have the quantum, in this case, the quantum C naught gate. And so this is ket psi, this is ket 0. And over here, we should get alpha 0, 0 plus beta 1, 1, 1. So notice that this is not violating the no cloning theorem because we are not converting psi to psi, psi, psi. This is therefore not in violation of that. So that is the encoding circuit for the bit flip code. And then let's assume that we have some channel that produces one bit flip error at most. So this is a channel that produces a bit flip error. And just like in the classical case, we have going to be having a syndrome detection. So we are going to have two wires over here at the bottom, which are ancilla wires. So here and here. So let me draw some ancilla wires. And again, we are going to have this sort of Z1 and Z2. So this is, sorry, not Z1, Z2, but this is the syndrome detection. This is ket 0, ket 0. And similarly, we'll have one over here. And so the syndrome detection happens over here. So this part is the syndrome detection. And then one can have the error correction based on these bits, based on the parity check of the 3 bits. Now, there is a slightly different way to look at this. We can look at this syndrome detection as a measurement process. And so we have this equivalence of, so the quantum C naught gate is equivalent to the control Z gate. So this can be checked with the Hadamard gates applied. All right, so I'm going to take the syndrome detection circuit and convert into this circuit, and then we'll have a measurement over here. Okay, so let's look at the equivalence of the syndrome detection circuit. So we have 3. So we have this circuit, which is Z1, Z2, and then right, this, because of this equivalence, can be, so we have Z1 and we have Z2 over here, and then we have the Hadamard gate. And then also we have, actually I should just write Z over here. So this is Z, another Z. And we have Z1, Z3, right? So we have this is the third. So this becomes an equivalent syndrome detection circuit. And here is what we have the measurement. Okay, so that is that. So what's the use of this? How can we take advantage of this equivalence? Well, if I look at the my Hilbert space of my of 8-dimensional Hilbert space, we have the following situation. So I can divide my um, 8-dimensional Hilbert space, which is consists of the code space. So I'm going to encode. So this is my code space 0, 0, 0 and 1, 1, 1. Then there is a space of exactly one error on the first qubit. So this will be my space where if the error occurs on so I'll call this E0. E1 will be if error occurs on the first qubit. So this will be 0, 1, 1. So this is my error space where the error occurs. So this space will get sort of rotated into this E0 will get rotated onto E1 if error occurs on the first qubit. And then we have the E2 if error occurs on the second qubit, which is 1, 0. So this is a span of this vector. So E2. And then we have E3, which is error occurring on the third qubit. Now, the equivalence of this sort of syndrome detection circuit is that the Z1, Z2 and the Z1, Z2, which is the Z operator on the first qubit, which is this one, and Z2, which is the Z operator on the second qubit, acts as a measurement operator on this space. And again, Z1, Z3, which is this and this, also acts on the measurement operator. And what measurements do you get? You get basically, again, just like the parity check, you get +1, +1, sorry, -1, sorry. So, which means that the measurement result is +1 if the encoded state has not changed at all. If you measure the Z1, Z2 operator, and if the third qubit is is flipped, then also you don't see a -1, but rather you get a +1. And in the case of the measurement using the Z1, Z3 operator, this is +1 and -1, which is essentially corresponds to the parity. So for instance, if I get an error on the second qubit, right, which means I'm in this E2 space, then the parity of the Z1, Z3 operator will be +1 and the Z1, Z2 operator will be -1. So that will uniquely determine that we are in this subspace. On the other hand, if let's say the error occurred on the third bit, then the measurement result of Z1, Z3 operator will be -1, whereas the Z1, Z2 will be +1. So we can uniquely determine. So this measurement operators, measurement results over here by measuring the ancilla bits, we are able to correctly detect the kind of error that has occurred. And one can also show this in a slightly different way. So if we have, let's say, an error occurring, so error is occurring on some error is occurring. Okay, so now you have and then this is my ancilla bit, then what does the syndrome extraction actually do? Well, one can look at this circuit, right? The circuit that I have drawn over here, this circuit essentially acts like this. So this will be identity over 2 plus Z1. So this is, I'm just showing for the Z1, Z2 operators. And similarly it will be the case for Z1, Z3 operators. So this will go over here plus identity over 2 minus Z1, Z2 over 2 E psi 1. Okay, so now let's assume that the error occurred on the first bit. Suppose the error occurred on the first bit, then Z1, Z2 E psi will be equal to minus E psi. So that is if, so the types of error we are going to correct is either identity x1, x2, or x3, right? Which correspond to these four subspaces over here, or partitioning our Hilbert space. And if the error occurs on the first qubit, then this equation will hold. So this will vanish. And so therefore, when you measure the ancilla bit, right, you will get a 1. And similarly, if let's say the error was on the third qubit, then Z1, Z2 E psi will be equal to E psi. And therefore, this will vanish. And the measurement result will be a 0, right? And you can do the similar analysis for the operators Z1, Z3. The point is that the measurement results over here correspond to the errors, and the errors actually correspond to which sort of subspace or which partition of the Hilbert space the original encoded vector has rotated into. So that will be how the error correction happens in the bit flip code. Now the phase flip is very, very similar. It's essentially changing all the Z operators to X operators. So for the phase flip, we do the following encoding. 0 goes to plus, 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 and 1 goes to minus, minus, minus. And the encoding circuit looks like this. There are just the Hadamard gates at the end over here. Right. And so the phase flip errors are again of three types, either no error or error on the phase flipper on the first qubit or Z2 or Z3. Again, our Hilbert space can be partitioned into essentially four partitions. And now instead of the error detection being done by the Z1 and control Z1 operators like this, let's say, this will be replaced by So the error detection will be done by the Z operators, and the Z operators, X operators. So this will change to this. And so the similar circuit, so what will happen over here, that if you take this circuit and replace essentially the Z operators by the X operators, we will have the error syndrome detection to circuit for the phase flip. And in the case of the bit flip, the correction operators are the X operators, whereas in the phase flip, the error recovery operators are the Z operators. So that's the main thing. And so there is a very beautiful theory of these error correction codes, which are stabilizer codes. So this points to the stabilizer codes, which we will talk in some other video. For now, we'll move on to the Shore code, which corrects both the bit flip and the phase flip errors. So just summarizing, let's summarize the quantum error correction. There are some challenges, for example, no cloning theorem, the fact that errors are continuous and measurement changes quantum information. Fortunately, quantum errors can also be discretized. Most of the quantum errors can be written as a linear combination of bit flip, phase flip, or a combination of bit flip and phase flip. And so the two types of errors that circuits that we learned in this was, one was the bit flip error, and the second was the phase flip error. And in the bit flip errors, we can write the syndrome detection circuit in the form of these operators, Z operators, which are essentially measurement operators. And what happens is that essentially the type of errors which we are trying to correct, which is either error occurring on the first qubit or single error occurring on the first qubit or second qubit or the third qubit, essentially partition our Hilbert space into 4 partitions. And the measurement of Z1, Z2, Z1 means Z on the first qubit and Z2 means Z on the second qubit. The measurement operators essentially are able to distinguish between these 4 partitions. So the syndrome detection part is essentially a measurement that allows us to distinguish between these 4 partitions. And then we correct the errors using the error recovery procedure, which will be our X operators. And for the phase flip operators, we encode using 0 goes to plus plus plus, and 1 goes to minus 1. So if a phase flip occurs, right, then plus goes to minus, right? So a phase flip on the first bit will result in minus plus plus. And so the same theory applies, except that instead of the in the detection part, the syndrome detection, instead of the Z operators, we use the X operators, and in the correction part or the recovery part, we use the Z operators.